just a reminder, there is a Math Society meeting that meets, I think at like 10 a.m., but I think it goes all the way till 1.
Do you get any credit for showing up?
I definitely do extra credit for like the talks, but where it's kind of this long thing. But I'll see you at chess club, right?
Chess club? Oh,
I think I will. That's today.
I have a given.
That's the thing. My thing will be
I think
sleeping.
I'll probably try to do something for chess club in addition to Math Society.
My thing's going to sleep and I've been up since 2 in the morning.
All right, the next thing we want to talk about are lines in 3D. But we need to be able to define lines parametrically. So before I even start talking about lines, I'm just going to spend a couple minutes reminding us what parametric equations are so that we can talk about lines. So just a reminder, taking a big step back, talking about functions and how they work. X was our independent variable. And X is allowed to be anything. Then Y is our dependent variable, and Y is going to be some sort of function, X squared. Then we can plug whatever X is into the function. Negative 2 squared is 4, negative 1 squared is 1, and I can go all the way down the list. And this created a coordinate with an X and a Y. And then we can plot all those points in one graph, and we've got a nice graph of X squared. If we talk about a parametric equation, again, we have always seen it where X is the independent variable and the Y coordinate depends on whatever X was. But for parametric equations, X and Y are going to be completely independent of each other. So now both X and Y are their own functions. They don't depend on each other. What they do depend on is some quote-unquote parameter, and hence why we get parametric equations. So now your parameter is your independent variable. It's allowed to be anything. And now the X coordinate depends on the parameter. So I can go ahead and plug t in to my X of t equation, and X of negative 2 is negative 6. X of negative 1 is negative 3. I can do this going all the way down the list. And now my Y of t and now I still get a coordinate, I still get an X, I still get a Y. So now I have the coordinate negative 6, 4, negative 3, 1, 0, 0, 3, 1, and 6, 4. So let's see if we were to graph this, how we can graph parametric equations. So I've got -6,4, -3,1, 0, 0, 3,1. But here's the thing that's different with parametric equations. I want to be able to illustrate and draw the parameter in my illustration. So we use t, the best way to think about this parameter is time. So this is some sort of animation that is drawing these points. At -2 seconds, you're at this coordinate. So we can go ahead and just kind of mark t equals -2. That's when in time that this point exists. Then at -1 seconds, you're at the point -3,1. And what we can do to help kind of convince ourselves of the motion of this picture is to sketch little arrows. So again, for these parametric equations, this is not a static image on the board. This is an animation, and it's going to be really great showing on the computer. It's going to be an animation of a point that moves through space at different times. And you can kind of illustrate the different times to see exactly when it's happening. So again, fundamentally, taking a big step back, it's a different for us than a function because x and y are independent of each other. We'll see visually in a second. That means this no longer needs to pass the vertical line test. You're going to have spirals and things that are bouncing all over the place. So go ahead and pull up Desmos, specifically pull up Desmos 2D. So here's how we're going to get parametric equations in Desmos 2D. You're going to type a coordinate, and you're going to type your x of t, or your x position, which was 3t, comma, t squared. So just peeking at this for a second, this is saying we're describing some point. So I want you to see that as a coordinate, x comma y, where x is 3t, and y is t squared. Desmos will automatically know that this is a parametric equation, and it will populate time values or parameter values to graph this between. So we can have this graph between 0 and 1. For the example that we just did, we were looking from -2 to 2. So why don't we go ahead and just change the parameters on Desmos from -2 to 2. And this is sketching this for all t values between -2 and 2. If we want to get a good animation going, then this is what we can do. Rewrite your parametric equations with, say, a, 3a comma a squared. And now you have a slider, you have some point that you can move left and right. If we want it to fit our existing one, then we can change A values to be between -2 and 2. Now I'm only gonna stay kind of locked in that area. And now here's the kicker, ready? Go up to your parameter at the very top and change the top bound. Have this drawing from -2 to A, whatever A is. Now when you move the slider, you can really start to see the animation tracing out this image here. If you hit the play button, it'll play on its own, but it tends to go backwards and forwards. We don't really like that. If we are thinking about this as time, we want it to move in only one direction. So if you hit this animation properties below the play pause button, you can have it move only in the forward direction. So it's gonna go from -2 up to your A value, and then just start over. So I do have a quick activity. What did you get when you plugged in 1 into this equation? Into x? When you plug 1 in for t? 3.
Yeah, it's modified.
So then just put 3. So now you have the coordinate 3, 1. Read it. Sure, but that one was already given. You want to now plug 1 into this equation. You're in degrees. Let's put radians.
probably given it's positive, the x of t. And now let's do, I don't know how to, it's also positive. So, at least.
So we only need it at 3.
Oh, okay.
So just plug in.
1, 2, so is that right? 33 and 27.
9 times 27. Yes.
But I think we have to do this look. But if you just look at this slopes of this graph, like this one here, something like that, t equals 2, we can let's see for a little like a little hole there, a little dot. And then look at the tangent line, it's going up, it's positive. And if you look at the curve there, it's equals 2 for the tangent line, and it's positive. So both of those sides are positive. If it's positive, anything.
What are we looking for? The signs of t.
Both positive. That's what I'm thinking, but I don't know. It's not. Wait, how do you work in this?
Yeah, so T1 is saying, how is the x coordinate changing? dy dt is saying, how is the y coordinate?
So it's not x is getting bigger because it's increasing in this between by our y is decreasing because from like 6.5 goes
And the dx dt is negative, it's x y is going negative as it's moving along the arrow, and then dy dt is positive as it starts going up.
Which one is that? I mean, any both of them.
I think this is
Two.
Wait, why is he?
So you see the arrows on your regions that are following along?
Yeah.
Yeah, t equals 2,
Oh, two.
the graph is following, so the x
T equals 2.
is going more negative, it's going left along the arrow, x value. But then the y value is moving up.
Like when it's coming back?
Yeah, let's look back.
2, 2. So 2 equals t, would that be like taking the derivative of 2t? Or,
for number 5.
yes.
Give me 2 seconds. I was gonna show that. Okay, so first, number 4, if you want the position at t equals 3, you can just find x of 3 and y of 3, just make sure you write it in order. Part B is asking, is the particle moving to the left or moving to the right? That is, how is the x coordinate changing? So if you have an x of t, that gives you the x position of the coordinate. I want to know, how is the x coordinate changing with respect to time?
That's right, we got
And x prime of 3 is positive. I don't care what the value is, x prime of 3 is positive. So this particle is moving to the right at that time. Another way of writing that, you could have written dx dt. It's just a different format, different notation. And that is the notation that I use for question 5. So I will try to sketch this on the board. So I've got my position moving like this. I've got an x of t and a y of t. I want to know the signs of dx dt and dy dt. This is saying at the given t value, how is the x coordinate changing? And just thinking left to right, x coordinate, if I'm heading in this direction, yes, my x coordinate is decreasing. So dx dt is negative. At this point, what is happening to my y coordinate? So only thinking up and down. The y coordinate is increasing. What questions do we have?
Is it because the exponent is like more like negative and positive? Is that what you're doing?
So don't think about this like in space. Just think you can only move left and right. At this point, are you moving to the left or moving to the right?
Yeah. So is this whole graph t equals 2 or that's one?
T equals 2 is just this point.
Okay, that's
That is the time when I'm at that coordinate. Questions? All right, so let's go ahead and save ourselves a nice, clean Desmos file. Just so every single time we don't have to kind of rewrite all the values. Write an f of t, write a g of t. Now you can have the parametric equation f of t, g of t. And if you just turn off graphing these two. Now you can just go up here and change this to be whatever you want, t to the third, and it changes in your coordinate. Then have the point f of a, comma, g of a. And again, now manually, you can just come up here and change it in your top equation, and it will change all the way through. Have the animation speed going only one direction. Once you're satisfied with what it looks like, go ahead and just save it. So now anytime you're working in Desmos 2D, you just have a saved parametric equations. You can just type it in and it starts animating for you. The only way for this stuff to kind of really set in is to just play around with this stuff. So again, I'm going to ask you over the weekend, just go home, play with these parametric equations all weekend, see what they look like. We should be able to recognize quote unquote famous ones. If you have cosine t, comma, sine t, and yes, if you had switched the order, you're going to get a circle. Because if you think about it, the cosine function toggles between -1 and 1. My y coordinates, the sine function, also toggles between -1 and 1. So if they're moving at the same time and bouncing back and forth, left, right, up and down at the same time, then you get a circle. So before I actually put this now, what happens if I put a 2 in front of my cosine? What if the x-coordinate now is allowed to be pulled out from -2 to 2, but y still stays fixed between -1 and 1?
It's gotta
Oh.
shrink.
We have a
back.
more precise word for that.
Oh, what was
It's an ellipse.
Ellipse, right. Oh, yeah. Ellipse.
What if I put a 2 in front of my sign here?
circle?
It's a circle. Yep. It's just going to increase the radius of the circle that you have.
That too. Right.
You can kind of play around with, what if I had made it negative? Just kind of changes the direction if you change sine to cosine. So again, play around with those parametric equations, but I am going to ask you to play around with parametric equations more in Desmos 3. So now we have an x of t, a y of t, and a z of t. So we have a 3-dimensional coordinate, all depending on some parameter. So for the first time, we're not going to see surfaces or paraboloids or planes, but we can see one singular point that traverses around. So think of this as a fly buzzing around the room, one singular point that moves through space. So I'm going to do the same thing, f of t, g of t, h of t. Alright, so before I finish graphing this, don't look. In 3 dimensions, what if I have cosine t, comma, sine t, comma, wait for it, t?
We have, is it on cylinder?
You're not far off. Don't forget, this is only one singular point now. Don't grab it, don't cheat it. I have, in the 2-dimensional plane, cosine t, sine t. So I have a circle. But this isn't yet.
Is it like a spiral?
That's exactly it. Like a helix, a spiral. So you've got cosine t, sine t, but now the t coordinate increases, excuse me, my z coordinate increases as time goes on. So now go ahead and graph that. Cosine t, sine t, comma, t. So now, remind me, what should I see if I look at this bird's eye view?
What's that view? Looking like a
See a
circle.
circle?
Yeah, you should see your circle. And when you change it back to that 3-dimensional view, you do see that spiral. And yes, if you change the z coordinate to cosine, but change, say, the y coordinate to t,
X.
you still get a spiral, but now just opening up along a different axis. So now if I look at the xz view, I still see my circle, but kind of letting it poke out a bit. Now I start to see the helix. What if I have cosine t, sine t, comma, 5, and just a number? Don't grab it, don't cheat. Cosine t, sine t, comma,
Oh.
5.
It's just a circle and the x
Well, that's it. So far, so good. Keep going.
I think since this, I think that the sign of 5 would be 0.
So we're all on the same page. If I peek down, you're definitely going to see a circle because your x of t and y of t are sine and cosine.
Okay.
But the z coordinate is always 5.
Just a
So it's
circle
just
on
around 5.
z equals 5.
Yep, it's a circle being traced around at a z value of 5.
Okay.
Delete one.
That's cool.
So again, this defines some sort of bug moving around through space. So imagine that we have that one singular point, but we don't want it to move all over the place, up and down, left and right. What if we just want it to move in one singular direction, and you're allowed to have this for positive and negative t values, then you get a line. And that's the goal. That's really where we're trying to get to for this lesson. If you said, what does a line look like in 3D? You have to define it parametrically. So that's exactly what we're going to do. This will be a 2-part lesson. We're going to spend the rest of class today and then all of Monday talking about lines. This is the first lesson that the number of questions that you can ask from it is going to be like a small thing. Just by slowly introducing lines, you get all the same questions from algebra, intersecting lines, parallel lines. So it will be a 2-part lesson. So let's go ahead and title this Lines in 3D. So in 3D, this is our general form of a line. So this is definitely our formal way that we want to be able to define a line. Summarizing it, since we're seeing it for the first time, the equation of a line in 3D is going to be a vector equation, or these things are defined parametrically, so you're going to have a t running around. To build a line, just like in 2D, you need a point and you need a slope. Slope is kind of a bad word to use in 3D. Slope means a number. The precise thing that we want to call this is a direction vector. So I need one singular point in space, and I need a direction, a vector, that tells me where this point is heading. And if I trace out all of the values in that direction, as well as in the negative direction, then you get a line. So to build a line, you need a point, and you need a direction vector. You can think of that as the slope. This says write an equation of the line containing a point with the direction vector. Looking over to what I just wrote in 3D though, you're like, well, hang on, you wrote the vector brackets. True, we can treat any point as a vector. So all we're gonna do is just treat that point as a vector. Plus t times the direction vector.
Why can you treat every point as a vector?
So any point can always be the vector in standard form from the origin. Now, my real answer is you can't add coordinates, but if you treat it as vector, you can add vectors. So just like lines in 2D, there are lots of forms that you can write them in. Point slope form, standard form, y-intercept form. So this is just going to be one of the forms that you write it in. Pros of this form is you can clearly see a point on the line, you can clearly see the direction vector. But since we know some vector operations, I'm allowed to distribute the t through. And now to add two vectors, you can add the x components, add the y components, add the z components. So let's title this one Vector Component Form. So now, given that that is a vector component form, notice the x, the y, and the z are all functions of t. In other words, this is some x that depends on t. This is some y that depends on t. That is some z that depends on t. Well then, we can write this as a parametric equation. So two forms that we have so far. This is a vector component form, technically. Just kind of cleaning it up and simplifying it, you can see it as one nice vector. All we're doing is just taking this and writing it as a set of parametric equations. X of t, y of t, z of t. So now let's run over to Desmos and type this in. where my x of t is -2 minus 4t. My y of t is 1 plus 2t. My z of t is 3 plus t. Now if we want to kind of ditch the animation idea, by default, Desmos will always prompt you to have parameters between like 0 and 1. Just put like -100, 200. It's just going to draw as far as it can. And that's going to be how we get a line in 3D. Now, just to make sure, we said that this line contains the point -2, 1, 3. So if I plot that, that should be a point on the line. Check. And our direction vector was -4, 2, 1. So here in red, can you see that? So here in red, I just kind of emphasized, this is the point, and I had Desmos sketch the direction vector, the slope of the line. And you can see that if you just scale this vector at any length that you want to, with any value of t, you get everything on this side of that point. Well, just making t values negative, then you can get all of the scaled versions on that side. Drawing all of the points forever, then you get a line. Please ask questions. Yeah.
Is there a dot to put for the vector at that point? It's like outside of the line that.
Say it one more time.
It's like the vector dot, like the Q or the D, it's like out Q.
So just turn that off, because that's just kind of the point.
Oh, so you don't really.
Yeah. The last form is kind of like the standard form of two-dimensional lines, which is, I don't really need it, but it is definitely worth showing. It does come up sometimes. So to get to this symmetric form, I'll write it at the very end when we get there. Kind of just ditch the x of t notation and just write x equals. And for each of these equations, solve for t. Once you've solved your x, you've solved your y, you've solved your z, solved all of those equations for t, then this is what we call our quote-unquote symmetric form. Since this is all t equals, you can say t equals x, y, and z. So again, we've got three different ways that we can write the equations of our lines. Vector component form, which you can either write as x of t, y of t, z of t, or you can write it in this idea, which is going to be some point plus t times your direction vector. Almost always, you're going to have to start in this form. You need a point, you need a slope. Let's first just exercise being able to switch between different forms. So I gave you three equations of three different lines. An equation in vector component form, a line written in parametric form, and a line written in this quote-unquote symmetric form. Take 2 seconds, write each of the equations in the other two forms. So for instance, for this vector component form, write it in parametric form, write it in symmetric form. So looking at just the first one, vector component form, I can distribute the t through. Now I can add the x components, add the y components, add the z components. This means x of t equals 4 plus 7t. Y of t equals just 5, and z of t equals negative 6 plus t. So two things to comment on here. A, you don't have to write the x of t notation. You might see something online where they write just x equals, y equals, z equals. I personally like the x of t notation. You don't have to write it. The second thing, do you have to show these two steps? No. You guys are going to do so many of these that you will be able to just look at this form here and immediately just be able to write, this is 4 plus 7t. Y is 5 and no t's. And z is negative 6 and 1t. And you can just write your parametric equation right after that. For symmetric form, we kind of drop the x of t, y of t, z of t notations, solve for t in each of them. We'll notice here, if applicable. Write t equals all of the things that t equals. If you have something left over where you can't solve for t, no worries, you just put y equals 5. Now again, this is a two-part lesson. I do hope to kind of uncover all of the different, well, what does this mean that y equals 5? What if it means that there's no t value there? It means that no matter where you go, the y coordinate is always 5. So let's go ahead and graph that.
So it's a vertical line.
Give me 2 seconds. Help me out. X of t is 4 plus
I'm sorry, where are we at?
17.
4 plus 7t.
y of t.
5.
That's right. And then z of t.
Negative 6 plus t.
You said negative 6?
Mm-hmm. But actually, yeah, that's right.
So I definitely have a quote-unquote normal-looking line, but if I look at this from my bird's eye view, the y value is always 5. The y value never changes. So when you start playing around with these lines, like I said, two-part lesson, we'll start realizing, well, what does that even mean if you get just a constant for one of them? Meaning that y value never changes. X and z change, but y doesn't change. So now if I have this parametric form, then I can write my vector component form to be 5, comma, 2 plus 3t, comma, 10 minus 6t. If you wanted to expand it, you could write this as 5, 2, 10, plus t times 0, 3, negative 6. Why would this be beneficial? You can clearly see a point that is on the line. You can clearly see the direction vector of the line. Now again, with lots of practice, you're going to be able to just look at these equations and I could ask, what is the direction vector? And you don't have to write it like this. You'll be able to just look at this and go, oh, it's the coefficient of t's. The direction vector is 0, 3, negative 6. And I can say, oh, well, give me any point on this line. And you go, oh, well, the point would be 5, 2, 10. That's a point on the line. Last thing I'll leave you with. If I give you parametric equations, you should be able to recognize if it is a line. And it's not too bad If everything is linear in X, Y, and Z, then you get a line. If I start asking, if I put cosines in here or anything like that, you get the fly buzzing around. If everything is linear, you get a straight line. I do have papers for you. The first one is parametric equations, practice problems. Just so that when you guys go home, you do have practice problems with solutions for just parametric equations. The next page, you have lines in space. This is the part one exercises. First question is just kind of getting used to rewriting them. The second one, given a point, given a direction vector. Flipping it over, I do want to leave you with a slight head start for number 3. Just a classic question. If I give you 2 points and you find the equation of the line, what's the only thing that I need from given 2 points to find the equation of the line?
Direction vector.
Yes, a slope or a direction vector. You can do that final minus initial, that gives you a direction vector, you have a point.
Ah, okay.
Sorry, all right, bye guys, we'll see you next week.
All right, thank you.